along the coordinate 1. Okay, and what is this? 1 defines the what is the stiffness when there is unit displacement along coordinate 1. What is the force or moment, okay, along the coordinate 1, along the coordinate 1. Now k to 1, k to 1. So this is what the stiffness. 1 is what when unit at coordinate 1 we have applied the displacement, unit displacement, and 2 is nothing but when we apply the unit displacement along the coordinate 1, what is the force and the moment develop along the coordinate 1, along the coordinate, along the coordinate 2, along the coordinate 2. That is the meaning. You got this one? This is very important, all the students. All the students, okay? Now this is very important, okay? So if you didn't understand what is the meaning of 1 1, okay, once again you take a screenshot of that one. This is very important throughout this 3 chapter, unit 3, unit 4, unit 5, unit 6, stiffness, matrix, and the flexibility, stiffness, and matrix method. This is very important. Now, so we'll find out this value of this K11, K12, K13, all these things. Okay. Now, our numerical is like this. That means along this coordinate, that moment, we have one coordinate. Okay. Similarly, here 2, 3, 4, 5, 6. Correct? Now, one by one we'll go. Now, first what we'll apply? We'll apply the unit. Now, one coordinate is like a moment. Okay. So, what we have to apply? Relation, you see. The moment gives us rotation, remember. And the force, vertical forces. Vertical force gives us displacement in vertical direction. Axial force, axial displacement. So now you see the coordinate 1 is like a moment. So what we have to apply? Unit rotation along the coordinate 1. Coordinate 1. So now, if we apply the unit rotation, this is theta. Okay. So the moment gives us theta, that is 1 unit. Okay. So what are the changes will happen along for other forces? Correct? That we have to see. When I apply now unit slope at the end. When I apply the unit slope at this end, what are the forces will generate at the end? We'll see. So in the last lecture we have seen when further end is fixed diagram. You see here, if the further see rotation without transport, only we apply the moment, that is unit rotation. Correct? Theta equals to 1. Okay. So what is the moment developed is 4 EI by L. 4 EI by L. I will keep paper like this. So when K11, what is K11 equals to, when the unit rotation applied along the coordinate 1, the moment generate along the coordinate 1 is 4 EI by L. 4 EI by L. 4 EI by L. Okay, now next, here also there is a coordinate 2, correct? So K21, K21. So when we apply the unit rotation at along the coordinate 1, what is the effect? What force developed at coordinate 2? You see here, it is half of that one. Half of that one. That is 2 EI by L. 2 EI by L. Now K31. 3 is what? 3 is what? Along vertical. So like this. Correct? So now you can see here, but when we apply the clockwise movement, the the force will be along that direction. The force will be along that direction. It is like this. But assume it is upward. So what? Minus. Minus. So what is 6 EI by L square? You got why it is minus? Students, why it is minus? You see, when we apply the moment like this, the reaction at this end is done downward direction, but we have applied the 3 along upward direction, so that's why it is minus. Okay, minus 6 EI by L square. Now K41, 4 is nothing but, again here we have upward 4 coordinates. Okay, now you see 4 is this reaction. When we have clockwise movement, this reaction is upward direction, correct? Upward direction. So we have plus 6 EI by L square. 6 EI by L square. And K51 is what? In axial direction. 5. In axial direction, when we have unit rotation at coordinate 1, there is no effect on the axial direction. So it is got 0. Similar 6-1 becomes 0. 6-1 becomes 0. You understood, students? This is very, these concepts are very, means you should clear this concept. Then only you can solve the numericals. And this is very useful throughout your career. Yes, students, you got this concept or not? This is very important concept. If you know this concept, then only you can solve the numericals. Yes. Students, it's okay. Okay, then we'll move ahead. It's no problem if you are okay now. So this line we have found. This line we have find out. Okay, already. Okay, that is we have applied the unit rotation at coordinate 1. Now next we'll see. Now second we'll apply the unit. Now 2 again, 2 also there is a movement, coordinate 2 also it is in along the movement direction. So we will apply the rotation, unit rotation along the coordinate 2, this theta, correct? So what is the movement? Here it will be developed along the coordinate 1, sorry 2, and here it will be along the coordinate 1. So what is the k11, sorry k, now we have applied the unit rotation at 2, k12. What is k12? Similar ulta diagram. So when we have unit rotation at 1, the moment developed at far end is half of that one, that is 2 ei by l, and k22 4 ei by l, and k32 3 is what here, 3 is positive. Now here it is downward direction, it is positive, so 6 ei by l square, and k42 is minus 6 ei by l square, and k52 axial direction 0, 62 is 0. Okay, students, okay. This goes up to direction, this goes downward direction, so we have minus and plus. The slope is on upward direction, the reaction also upward direction. Here slope is downward direction, so reaction also downward direction. Okay, remember this. Okay, now so the next one. Now what is third one? We'll apply the unit. So what is the third? Third is what? The force. So we'll apply the unit displacement along the coordinate 1, sorry 3, delta equals to 1. Okay, so what we have to find out, this force along 3, along 4, what is the moment along 1, what is the moment along 2, and the axial deformation, Now this already we have seen. See here. See here this diagram. Correct? I'll keep like this. See here, already we have seen this one. Okay, so when we have unit displacement along this one, the P force gives us 12. Now what is K1? Now along 3 we have applied K1 3. So what is the moment? Moment is 6 ci by L square. Now moment is anti-clockwise. Moment is anti-clockwise, but the coordinate one is clockwise. So minus 6 ei by L square. Okay, and what is K 2 3? Here also it is anti-clockwise. Same moment, anti-clockwise, minus 6 ei by L square. What is the K 3 3? Along the coordinate 3, what is the force? Develop 12 ei, upward direction. So plus. And what is the K 4 3? The force is in downward direction, but we apply upward, coordinate 4 is upward, so minus 12 ei by L cube. 12 ei by L cube. Correct? Correct? No. So that's why I told in the last class you should know these diagrams. Okay? Now, fourth one. Now the unit displacement along the coordinate 4. So what we have? This one. It will be like this. So delta equals to 1. The moment will generate like clockwise, here clockwise. The reaction is downward direction. Okay, student, now this one. So we apply delta 1, upward direction, moments are clockwise. Simple. Now K in 4 direction. In 4th coordinate along the 4, we have applied the K1 4. K1 4 clockwise plus 6 ci by L square. K2 4 clockwise 6 ci by L square. K3 4 now downward direction minus 12 ei by L cube. K44 positive 12 ei by L cube, and K54 equals to 0, K64 equals to 0. Because when we apply the displacement along vertical direction, there is no effect on the axial direction. Okay, there is no force developed in the axial direction. Okay, now and the last one now. Fifth one, the unit displacement, that is called as axial displacement, along the coordinate phi. Now we have applied the delta equals to 1. along phi. Correct? So this also will move like this. Correct? So all when we have axial displacement, there is no force generated along and moment is generated. So K1 phi equals to 0, K2 phi equals to 0, K3 phi equals to 0, K4 phi equals to 0. Now K5 phi. When unit displacement at along the coordinate phi, so what is the force developed at phi? So axial is AE by L, and K6 5. Now when the displacement is like this, then when force is applied like this, so to resist this force along 6 we have force up in opposite direction, but the 6 coordinate we have assumed like this. Okay, so that's a minus A by L, minus A by L. And the last one, 6 applied unit axial displacement along the coordinate 2, so coordinate 6. So when we have to apply the force like this, okay, 6. So this gives us in opposite direction. So all the forces K16, K26, K36, K46 equals to 0, and K56 minus A by L, and K66 plus A by L. Okay, now so after solving all these things, it comes into the matrix format. So I'll keep all the paper aside. So what is K11? What is K11? You got 4 EI by L. Okay, EI by L. K21, 2 EI by L. K31 minus 6 EI by L square. K41 plus 6 EI by L square. And next K51 0, K61 0. Now K12 2 EI by L. I will write like this. K22 4 EI by L. Okay. K31, so K32 minus 6, sorry, K32 minus 6 EI by L square. Now K42 plus 6 EI by L square, 0 0. Now K41, sorry, K14, okay, sorry, K13 will be minus 6 EI by L square. K23 minus 6 EI by L square. K33 plus 12 EI by L cube. Then K43 minus 12 EI by L cube, 0 0. Next K14 plus 6 EI by L cube, L square, sorry. K24 plus 6 EI by L square. K3 4 minus 12 EI by L cube. K4 4 plus 12 EI by L cube. K5 4 0 0. K5 1 0 0 0 0. Only we have A by L minus A by L. And in 0 0 0 0 minus A by L plus A by L. So this is what our 6 by 6 matrix. This is our 6 by 6 matrix. Now you can observe the things. So this is what the diagonal. Correct? Now the upper matrix above this diagonal called as upper, above this one called as a lower. Upper and lower matrix are same. See here 2 EI by L, 2 EI by L. Minus 6 EI by L square, minus 6 EI by square. Minus 6 by minus 6. Plus 6 EI by L square. Plus 6 EI plus 6 EI by L square. Minus 12 EI by minus 12 EI. So the upper matrix and lower matrix are same. Upper matrix and lower matrix are same, and this is called as a diagonal matrix. So when the matrix stiffness matrix or flexibility matrix will form, in the finite element method, the upper matrix must be equals to lower matrix. Remember this. Okay. So this is what the formation of the matrix when we have numerical like this. Okay. Okay, students. Students, okay now? Okay. So now we'll come to our original. Now we'll see the relation between stiffness and the flexibility matrix. Okay. So we know the stiffness is equal to force per unit displacement, and the flexibility equals to displacement upon force per unit force. So when you multiply K and delta, K into delta, so what will happen? P divided by delta into delta divided by P, it becomes 1. It becomes 1. So what we have to show the relation, that is the flexibility matrix and the stiffness matrix, if we multiply, so we will form a unit matrix I. We will form the unit matrix, that we have to show the relation. We have to prove that one. How to prove? We will see now. Now the proof. Okay. Okay. So this is what our regular format. That means how we can judge like this. So we have to prove that one in the matrix format. Okay. So the force displacement relation may be expressed by the matrix equation, that is delta equals to flexibility matrix into P matrix. That is what here delta equals to flexibility into P. Okay. Now multiplying both sides, by delta inverse, flexibility inverse matrix. Okay. So what is delta inverse equals to inverse okay. Now, so what is this gives us inverse matrix, and this one gives us 0, sorry 1. So I can write P only. I can write P only. Now we know inverse of stiffness matrix must be equals to, sorry, inverse of flexibility matrix must be equals to the stiffness matrix. Correct? Correct. So what we'll do, here for this equation we will multiply both the sides by delta, multiplying both the sides by flexibility matrix. So what is delta? Delta inverse equals to delta and the stiffness matrix. So this becomes what? Unit matrix equals to delta and k. Simple. Okay. So this is what the proof. Okay. Okay, students. So this is what the relation between stiffness matrix and flexibility matrix. Stiffness matrix and flexibility matrix. Okay. Now, okay. Next we'll see. So what to form to solve this flexibility method? We'll see now. So force method, also called as flexibility method, also called compatibility method. Remember this. So flexibility method has three names. It is also called as a force method, flexibility method, and compatibility method. Okay. And for the stiffness method, we call as a displacement method or stiffness method or equilibrium method. So you should not be confused when in numerical, if they told or given it is solve this numerical numerical by force method. That means you have to solve by flexibility method. Solve this numerical by compatibility method. That means it is a flexibility problem. Solve this numerical by displacement method. That means it is a stiffness problem. Solve this numerical by equilibrium method. That means it is a stiffness problem. Okay, students? Okay. Now, what is actually the difference between flexibility, that is force, and displacement method? We'll see. Okay. We'll see the comparison. We'll see the comparison. Okay. So here I will write force method. In bracket I will write flexibility or compatibility method. Here I will write displacement in bracket I will write stiffness or equilibrium method. Okay, so we'll go one by one. The first one, determine the degree of static indeterminacy. Determine the degree of static indeterminacy. MINC1. Okay. So when we are solving the force method, you have to find out the static indeterminacy. And in the displacement method, determine the degree of freedom. The degree of freedom. That is also called as a degree of kinematic determinacy. Kinematic determinacy. Okay, that is the first step. Now in the second one, the second step in the force method, choose the redundant. Choose the redundant. Okay, and in the displacement method, identify the independent displacement components. Identify the independent displacement components. Displacement components. Okay, now third step, assign the coordinates. Assign the coordinates 1, 2, 3 up to n to the redundant to the redundant third. In the third step, assign coordinates 1, 2, 3, and to the independent to the independent displacement. Independent displacements. Okay. Now the fourth step. What is the fourth one? Remove all the redundants. Remove all the redundants to obtain the released structure. I will explain all these things. So you should write all these things. Released structure. And here, fourth step, prevent all the independent displacement. Prevent all the independent displacement. In the independent displacement components to obtain the restrained structure. That means this one we are making the determinant structure. Okay. By releasing all these things, and here we are making fixed structure, rigid structure or rigid structure. Rigid structure. Now next. Fifth one, determine delta L. That is what? The displacement at the coordinates okay, displacement at the coordinates due to the applied loads. Applied loads acting on a release structure. Acting on the released structure. Okay. And here fifth, determine P dash, the force required at the coordinates at the coordinates in the restraint structure due to the loads other than those acting on the coordinates. That means we have to remove the loads along the coordinates, and whatever the loads on the span, we have to find out these forces. Okay. Now, sixth one, determine delta R. What is the meaning of delta R? The displacement at the coordinates due to the redundance acting on the release structure. Here 6, determine P delta. That is the force required at the coordinates. That is the force required at the coordinates in the unrestrained structure to cause the independent displacement components delta. Now the seventh one. Calculate the net displacement at the coordinates. Calculate the net displacement at the coordinate. How? By using this formula, delta equals to delta L plus delta R. Okay, and here 7. Calculate the net forces at the coordinates. Here what? P equals to P dash plus P delta. Now next one. Now the next one is 8. Use the condition of compatibility. Use the condition of compatibility of displacement to calculate the redundant. to calculate the redundant. That is P equals to inverse of flexibility matrix, here delta minus delta L, closed semicolon, and here eighth use the condition of equilibrium of forces to calculate the displacement. So here delta equals to inverse of stiffness matrix P matrix minus P dash matrix, closed. And the last one, ninth, knowing the redundants, calculate the internal member forces by using equation of statics. And here ninth, knowing the displacement, calculate the internal member forces by using slope deflection method. Okay, so like this. So these are the steps involved in the stiffness and flexibility matrix. Okay. Okay, so I think you can take a screenshot of those things. Okay, so we'll stop here and we'll meet in the next lecture. The time is over. Okay, so you can leave the meeting.